and noncommutative geometry.
Okay, thank you very much. Thank you for the invitation to give this talk. I want to talk about loop groups and noncommutative geometry, but I think a subtitle could actually be Subfactors, K-theory, and conformal field theory. So the title of this program, because I will mention all three of these topics at some point. So you can say talking about some combination of all of that. And it's also good that we had this talk about, well, that we had loop groups already in the previous talk and a bit of fusion, because that will be one of the ingredients that we will need today. So what is this mainly about? So the idea is that we have loop groups with their representation theory. So what we're usually interested are projective unitary strongly continuous positive energy representations, because they are interesting from a physical point of view, also mathematically, and because we can say a lot about those in general. There are lots of other representations which are quite ugly from that point of view, and we're not concerned too much about those. So that's what I mean by representation theory. And on the other hand, there should be noncommutative geometry, and by this I mean things like spectral triples. So that's the basic building stone of noncommutative geometry. Out of that you can develop lots of other things, and to some extent also K-theory. And the way we go from here to here, well, so the main part in my talk, first I will give some preliminaries, but then the main part will be about the idea of this construction, how to get out of loop groups some non-commutative geometric quantities, invariants or something. So how we can go from here to the right side, and the idea behind that comes from conformal field theory, more precisely conformal nets, where we have subfactors also. Okay, so that is the idea. And maybe I should stress something else also, that I was not primarily interested in loop groups, although that's mainly the title of this talk, but all this arose out of a study of conformal nets from the point of view of noncommutative geometry. So that's something that has been going on for quite a few years, how to understand conformal nets, possibly with some kind of supersymmetry, from the point of view of noncommutative geometry. Now, as we've seen in the previous talk also, that loop groups give rise, well, in nice cases, loop groups give rise to conformal field theory or to conformal nets, and so they form a particular example. And in all these studies over the years, it has turned out that loop groups are possibly the best examples, the nicest examples, where all things that we construct on this side nicely merge together. So that's why I want to talk about loop groups. And the first part, we need not know anything about conformal nets at all, although it makes it a little bit better to understand if we have some knowledge about it. Towards the end, I will mention a few more facts about more general conformal nets, which don't come from loop groups, and that should conclude everything then. Okay, so as I said, first some preliminaries. Okay, what we of course need is the loop group. Well, let's say G should be a compact, simple, and simply connected Lie group. We have finite dimensions, and then we form the loop group out of that, which we define as the smooth maps from a circle into G. And we take pointwise multiplication and we take the C infinity topology, which makes it a topological group, and in fact a infinite dimensional Lie group in some sense. Okay, then so one example that we've seen before is where we take G equal to SU2, so that gives us probably the first example that one would study if one investigates this. Okay, then I said we're interested in projective unitary positive energy representations. Okay, so that is the kind of representations that I want for my loop group, and more precisely so to this Lie group G there's a corresponding Lie algebra, finite dimensional Lie algebra, and for that Lie algebra I can form the loop Lie algebra and consider central extensions, and that gives me Lie algebra of LG, and this, well, this affine Kac-Moody algebra that I get this way has certain representations, and we're interested in the highest weight representations that come from those algebras. So I write here more precisely those arising from highest weight or lowest weight, whatever our setting, highest weight unitary representations of the corresponding affine Kac-Moody Lie algebra. So I denote that in this way. Okay, so in this affine Kac-Moody Lie algebra, there is a designated element designated central element, which I call CG, and we call L, maybe L pi, and the level of the irreducible representation pi as above. Okay, so if you take such an irreducible highest weight unitary representation, then you study the value of CG in that representation. That will be okay, for these kinds of Lie algebras, that will be an integer, and that will be the level. Okay, so that is also a quantity that we will use. Okay, so that is the setting. Pardon?
What is the energy?
The energy you get as the generator, the infinitesimal generator of the rotation action on the loop group. So that there would be an energy operator also in here. Okay, so the last thing that we need for loop groups is that following. So let pi I be the equivalence classes of such irreducible representations, and so my I runs from 0, say, to some n minus 1 if there are n irreducible in equivalence classes of irreducible representations of my loop group, so representations of this kind, and they give rise to a semi-ring. So the addition would just be a direct sum of representations, but there's a product structure, this fusion product, where k goes from 0 to n minus 1, and nij k are called fusion coefficients. Okay, and so the corresponding ring that I get from this semi-ring, one calls the Verlinde fusion ring. Okay, so that is the ingredient that we need here. Okay, so we've heard about fusion already before. You can get these fusion rules in various ways depending on what setting we are. In that case, usually one uses the operator product expansion, but if we go to the language of conformal nets, which I don't want to do right now, if we go to the language of conformal nets, you get that from fusion of the so-called DHR sectors. So that is how one can get these rules. And okay, so that is, sorry, I have to say here, at fixed level L. So I study all the irreducible representations at a fixed level, which have a fixed level L, so which satisfy this rule, and then I have such a ring structure. Okay, so that's the first part. And we look at the right hand side now, and so the basic ingredient that we need for noncommutative geometry would be spectral triples, and to be more precise, we say a Fitter-summable even spectral triple consists of the following: an algebra. Okay, it could be any kind of algebra. Often one wants a little bit more, like a locally convex algebra or even Banach C-star algebras. But in this setting, just say an algebra. Then a representation of this algebra on some Hilbert space. On a graded Hilbert space H pi. So the grading comes from the fact that we study even spectral triples. If we study odd ones, we don't need the grading. Such that if you look at the algebra in the representation, so acting on B of H pi, say by, so a Z2 grading to be more precise, by a self-adjoint unitary on H pi. You study the commutator, and this should vanish. So in the representation, all the algebra acts as even operators, in the sense that they commute. Okay, and the final ingredient, so a self-adjoint operator D on H pi unbounded, densely defined, such that such that pi of A lies in the domain of the derivation associated to D. Okay, where is the derivation arising from D. So you could study the commutator of D with elements. Moreover, I need that this D is an odd operator with respect to the grading, and finally that e to the minus D squared should be a trace class element. So this one, I can take the trace of this operator for every positive t. And this means this is the meaning of theta summability. Okay, so that is what we need as a spectral triple. Maybe as the standard example that you could, where this comes from actually, I think most of you will have seen this before, but just for completeness, where this comes from is that in the commutative setting, so for commutative manifolds, you would study the algebra of smooth functions on the manifold that corresponds to A. Then you would study the the regular representation on some spin-off bundle possibly, or on the algebra itself, on the manifold itself, as you like. That would be pi, and then D would be some kind of Dirac operator on that manifold. So that would be the commutative setting, and that's Kahn's generalization to the non-commutative setting, and it has helped in many cases to understand non-commutative algebras with some further geometric structure. Okay, so that is the kind of structure that we will get here. The next thing we'll need is K-theory. So since there's not too much time, just maybe now let A be a C-star algebra. Then I define this just as the group generated by classes, equivalence classes in the sense of Murray von Neumann, of projections in M infinity of A. Okay, so you take infinite matrices with entries in A such that only finitely many entries are non-zero, and then you put in those entries projections in the C-star algebra A, and okay, then you study equivalence classes of those, and in a good sense you can add them up, but putting them in a correct way there. Okay, then we need something like K homology, which you can call in a vague sense dual to that, and I call this the group generated by even Fredholm modules for A. This is particularly vague, and I want to leave it at that. The last part is K theory, which comprises actually the first two ones. So this is pi variant. You have two C-star algebras now, and you study some group generated by Kasparov AB modules. So this should be a graded Hilbert B module. This should be a map from, well, homomorphism from A into here, and here we have some operator acting on my Hilbert B module and having some further properties. Okay, so why I need this all is that there are special cases. You can imagine special cases where you study you study the case, what I want to say. Let's do first the following. There's a product structure. So a priori this is just a group, but then there's some further appropriate assumptions on the C star algebras involved here. One can define this a product, which takes a group for AB, another group for BC, and gives an element in the KK group of AC. Now, if you choose all algebras the same, then you can interpret that as a group structure, well, a product inside this KK group, and which turns it therefore into a ring. And that is the idea that we will use later on, because we will need some kind of ring structure. Okay. Particularly nice is the case where you study endomorphisms of an algebra A, and you take all three algebras the same, and then for such an endomorphism you get an element in here, you get an element in here, and it will essentially correspond to the composition of such endomorphisms. Okay, that is not the general case of the KK product, otherwise it would be boring, but in our situation that will be what we will essentially need. Okay, and the last point that we need is an identification. Okay, and this means that I can involve the K homology groups and the K theory groups into this product structure, because I can see if I take as one C star algebra just the complex numbers, I can compute the products for those. Okay, so that is what I need as ingredients. And now we can come to the actual construction. Okay, so what we wanted to do is we start with a loop group, and we know the representation theory, we know the fusion rules, we know them from whatever you start with, operator, product, expansion, or if you start in the conformal field theory case, in the conformal net case, you have them from somewhere else. So these fusion groups are known for the loop group, and out of that we want to get quantities like here, spectral triples, K classes, and so on. Okay, so the idea here is we define the following algebra. we take the direct sum. Here we take the representations of my loop group. I take the bicommutant, and well, this bicommutant, since it's an irreducible representation, this will be just a b of h, so a summand b of h, and I sum that up, and I get n copies of b of h. It doesn't look particularly exciting, but that is what we need as our universal algebra, let's say, C star, or even von Neumann algebra. Then out of that, this is quite big, since it contains copies of b of h, so it's not nice from the C star algebraic point of view. But out of that, we can study the intersection of this algebra with a compact. So this is a direct sum, it acts on a direct sum of Hilbert spaces. So the direct sum Hilbert space can be taken in order to define what's a compact operator. And that's what we need here. So we intersect this with the compact operators, which will be isomorphic to a direct sum of compacts. So what is the point of all this? Because it looks somehow ad hoc, why do we use that? The idea behind that is that, as I said, the motivations come from conformal nets. And when you have a conformal net, maybe, so let's draw that here. Just a reminder, so a conformal net is a mapping from the set of intervals, so well, particular intervals, to von Neumann algebras. So for every interval on the circle, you have a corresponding von Neumann algebra with some further properties. So for example, if you include one interval in another, the von Neumann algebra should be included, and you have some geometric group action on that. And okay, so that is the setting. So one usually has a family, a very big family of von Neumann algebras, and to that family one can define what's a representation of those nets, but it's a huge collection of nets, and therefore sometimes it makes sense to go to one algebra instead of an infinite family of algebras. And that one algebra that one considers is the universal C star algebra generated by all local von Neumann algebras with a property that the representations give rise to representations of that C star algebra and vice versa, so that you can have a correspondence between the locally normal representations of the net and those of the C star algebra. Okay, and when one starts to compute the C star algebra, the surprising result is that one gets up just with a sum of such, well, b of h's. And yeah, that is quite surprising, because the definition of this universal C star algebra does not rely on such a structure at all. One would not expect that. And since the representations of my net, which would correspond to the loop group, so a loop group net would come from the loop group representations, since that has this correspondence with this universal big C star algebra, I can use that idea in order to arrive at this definition. Okay, so that is a natural choice, a very natural choice of an algebra to take. And so the representations of my loop group would then correspond to representations of this algebra. And in fact, one can show that they preserve this subalgebra of compact operators. That's a nice separable subalgebra, and I can have all the fusion ring structure on this smaller algebra, and that is what we will take now. Second point that we need, since we want to construct some kind of spectral triples, these loop groups have no supersymmetry so far. There's no kind of grading. We don't know what is an even, what is an odd element, and all that. So what we do is to add some fermions. Fermions we had in the previous talk already. Fermions in the sense of CAR algebras, more precisely. let D be the dimension of my group G. Then we consider self-dual CAR algebra with D free fermionic fields. So that's the C-star algebra generated by these anti-commutation relations that we've seen previously. And okay, and then you consider the so-called graded Raymond representation of this. I won't specify what is that representation. It is a particular kind of representation that you get for the CAR algebra. Okay, and with that, I define the following representation. So I represent the loop group, so this universal algebra for the loop group on B of H okay, so I take the product space of my Raymond representation for the fermion and the particular representation that I'm interested here for the loop group. I take the product space and I represent the loop group not on its original space but on this tensor product space with the Raymond representation. But on the fermionic side I take just a fixed projector. So this representation is not unital. That is important. But for the rest it's a representation, so I can do everything that I want. And the nice thing about this is that if I take this Raymond representation with D fermionic generators together with this loop group of dimension D, then I can get out of that a canonical Dirac operator. And that will be the element that we need here. Okay, so out of that, you get a Dirac operator, and hence a spectral triple. Okay, so maybe I summarize this now in a.
And for the first property, that the universal algebra is the sum of B of H, do you need complete rationality or something weaker? Which is for
Yes, you need complete rationality. But so we can assume that for these loop groups, you know it for SUN, but let's assume it for other loop groups as well, that the corresponding net has this property. That's in the net language. But if we do this so here you don't have any nets at all, so you don't need that. You just take the representation of the loop group and you know that there are finitely many, and then it is okay.
Sorry, how does it depend on the choice of this ER of the projection there?
Pardon?
How does this phi hat should depend on ER?
So ER should be a one-dimensional projection onto an odd part in your Hilbert space, but apart from that, there's no restriction. So if you change it within that restriction, you get the same.
This is just a stylistic comment. Instead of saying we can assume that this holds, I think it makes sense to acknowledge that this is an important open problem.
Yes, it is.
Very important in the area. So it should be advertised.
I wanted to advertise that towards the end, but now I can advertise it now that there's an open conjecture to saying that the fusion ring in the sense of loop groups is isomorphic to the fusion ring that we get in the sense of conformal nets. So this has been proved for the case of SUN. So in particular, this example of SU2 matches all the conditions that we need. But in general, it is an open problem. So I should also acknowledge the people who proved that, since they are in the audience. That should be Anthony Wasserman with Feng Shu, if I remember it correctly. Okay, so that is what we need here. But in other cases, it is widely believed to be true. That's why it's called.
I mean, Valerio Toledano Laredo, in his thesis and a subsequent thing, explained how to do it for loops on SON as well. SON.
SON. Okay, so we can.
Essentially by the method I was talking about. Where he used this Patev-Totsenko differential equation.
Okay, thank you. So, but in general, we just assume it as a conjecture. I think most people don't doubt it. Okay, so that is what we. Who doubts it?
Perhaps there are some people who think they can prove it. So I don't
Okay, they can give.
level of
They can give the next talk then. Actually, I forgot to say something here. Also, in order to acknowledge people in the audience.
The construction does not depend on the conjecture, just the derivation.
So out of such an even theta summable spectral triple, you get a JLO entire cyclic cocycle. So one of the authors is also in the audience, and that is somehow the non-commutative analog of the Chan character that you have in classical geometry, and therefore it gives you let's say a cohomological invariant of your non-commutative manifold. So once we get a spectral triple, we automatically have these cohomological invariants.
The other two are Lesniewski, Osterwald.
Pardon?
Lesniewski and Osterwald.
And Osterwald.
Osterwald.
So I should have removed the J.
No.
No, I don't remove it.
You have to add.
Okay. So first theorem, to summarize that. So under these assumptions that we have our loop group like that. So for every class of irreducible representations, of LG, there is a corresponding even theta summable spectral triple giving rise to a JLO cocycle okay. Pardon? Pi hat. Thank you. Giving rise to a JLO cocycle and some characteristic projections Pi. Actually, this should not be A, this should be BGL. No, it shouldn't even be GL, it should be K. K1 GL. Where K1, so are the elements in KGL. Maybe I should. Okay. So there are, this Dirac operator gives rise to a derivation, and this derivation acts on certain elements where it is defined, and I take the ones in here which are in the domain such that the image again is a compact operator. So I don't want to define it as in some sense differentiable elements inside my compact operator algebra. And this is what I want here. Because in the end, we need the property that A is inside the domain of the derivation. So I need some kind of differentiable elements. Call that K1 GL. Okay? And there should be my characteristic projections. Now we see projections. Okay, one has to work this out, of course, but they give rise to classes in K0 of, here you put KGL1, and then you have some elements in here. Okay, and this gives rise to a pairing. Where you put the ith J-Oko cycle, and here the class, let's say the Jth projection, characteristic projection, and that is just delta ij between 0 and n minus 1. So using this, I can get spectral triples automatically for my loop group, canonical spectral triples, and out of them I get cohomological invariance, and I can recover the representation which I have here by pairing it with these characteristic projections. So I just pair it with all of them until I find out what number is I. Okay, that is the first part. So that gives us the first kind of non-commutative geometric invariant in terms of cohomology class. But we can actually see that this J-Oko cycle can be interpreted as a K-homology class, while the projection can be interpreted as a K-Fury class. So you have a pairing, pairing between these two here, and that is the the second part. So the second part is layer maps from the fusion ring inside. So let's take the order right. So here I can leave away the 1 in order to get a C-star algebra. This one is usually not a C-star algebra, but I can take this one and I have my C-star algebra and no further problems. So I get 3 maps. Where the first one is a group isomorphism, second is a ring endomorphism, so the ring structure comes from the Kasparov product here, and the last one is again a group isomorphism, which is uniquely determined by the property. So let's get this. So if you take x and y in my fusion ring, then this is just phi 1 of xy. So this one, essentially, this one acts on this one, which determines the relation. And the second one, if you take the conjugation, that is an operation that we have in the fusion ring, and you have this relation. So that defines it uniquely, that determines it uniquely. And we have the following relation. Now we can put them all together. Namely, we take okay, so we have here something in the K homology, here something in KK theory, and here something in K theory. And I take maybe the kth, the ith, and the jth class in here, and they pair together by giving me exactly the fusion rules. So what does this mean? I can interpret the fusion product as a Kasparov product. So in this sense, the fusion product is nothing else than a product in here where we choose appropriate algebras. And that is the basic statement we can see here. And we can use that, maybe if we know two of them, we can use that in order to recover the last one. Okay, so that is the main statement. So somehow the fusion rules, the fusion ring itself, seen as a group, is not particularly interesting because it gives you just something in K0 of KGL, which will be, so we know that the K0 group of the compact operators of one copy of the compact operators is just Z. So this is just a direct sum of Z's, Z to the power of n. So the lattice of n-dimensional lattice of integers. That's not particularly interesting. The interesting part is seen in the way this embedding works. So in the way the fusion ring embeds into the KK group. If you change the embedding, you change the fusion rules. Even if you take the same number of representations, changing the embedding changes the fusion rules. And so this way, the fusion product can be seen as a Kasparov product. Okay. So I think I have 10 more minutes. Any question about this so far? Because I wanted to say little bit more what we can do with this.
Constructed by zero, you use the
Pardon?
already use that you know the nijk, right? So you use that as an external input. Yes.
Yeah. But yeah, we said we started from the beginning that we know already what is the loop group. You know already what are the fusion rules and something. It just
Also
gives.
the KK ring is just a matrix ring.
Yeah.
You have UCT. So I think that you're just translating the Verlinde ring into a slightly different language, but just formally without doing anything.
Yeah.
You have some explicit analytic formulas for these maps phi. You have just something like chosen a basis for this Verlinde ring and written down the
together with,
and then you have identified KK groups also with the same basis, so you don't seem to learn anything from this exercise. Also, your theorem about this pairing, well, since spectral triplets on the compact operator just, all the information is in one index computation. So somehow out of this representation, this Dirac operator D has somehow index 1. So somehow you manage to construct an operator of index 1. I would guess
the Dirac operator has not index 1, no.
Well, after you cut it down with projections, because that's
okay. Once you cut it down, you can compute some.
You cut it down by the appropriate projections, which you should do when working with compact operators. You get an index 1 operator, and I would guess that most of the work is done by this Carr algebra, because also usually, you use these Clifford algebra stuff to produce things with some index. So the loop groups don't seem to play much of a role in this construction.
No, they don't play much of a role as such, because I will show now that we can do that also.
This n equals 1. I mean, the character formulas for these things are defined by such Dirac operators in n equals 1 supersymmetric algebra. So that's kind of a rather well-known thing of Godot, Kent and Olive, ancient history.
yeah, as I said, the original way where we want to learn something comes from the language of conformal nets in more generality, and it is just that in the case of loop groups, and as I show now in a few other examples, you can work out everything, and use this way to represent it in non-commutative geometric language.
Maybe I just have a rapid comment on this, because I think it's essentially, the point is true. So we don't try to write something, but we want to write something in a certain way, so we have a certain interpretation. You're right, you can construct many Dirac operators that make the same job, and so loop groups is not around because around the algebra. But we can write this explicitly in terms of quantum field theory object. This is the point. So we have, so of course, you can change the construction, you get the same, but okay, that's
Okay. I continue for the last 5 minutes. So first of all, I wanted to say, so the loop groups is just the first part. Out of that, you can construct further models by changing this definition here a little bit. So instead of taking the loop groups with the Carr algebra over D generators or D free fermionic fields, one can introduce the notion of a superconformal tensor product. Okay. So I generalize this to conformal nets. Which admit superconformal tensor products. I won't say what exactly this is, but the loop groups would be an example for that, because you can take the Carr algebra and put them together in order to get something which is superconformal. You have an action of the super Virasoro algebra as symmetry group. Okay, so I want nets which have this further property, and then using that and going through the proofs again, which I haven't presented, but going through the proofs again, you get the same, essentially the same theorem again. In that case, of course, you would have to take as our fusion product the product that comes from conformal nets, so DHR fusion ring, not the Verlinde ring. It doesn't make sense in those settings. If we go back to the conjecture which Andre mentioned before, so that helps us to put these two things into relation for one another. So generalize this to conformal nets, and then one can study products. So if I have two such nets, I can put them together. They would automatically, let's consider the tensor product net. That would be automatically, again, an example for that. I could study irreducible local extensions. Once I have such a net, I can study extensions of that net. In particular, the product net allows me, so if I have, let's say, if I have n loop groups in the sense that I had here before, which are simply connected and compact, I can take the product and have more general loop groups this way. I can even study the particular loop group doesn't fall into the category U1. So U1 works. And one studies extension of that, and one finds that, on product extensions, finds that lattices work. So lattices, which you get as extensions of U1. One can show that cosets coset nets work. So that is for people who know about conformal nets, this language. So for the coset net, I have something. And then in particular, as examples, the Virasoro net. So the Virasoro net is in some sense the minimal net, in the way that every diffeomorphism covariant conformal net has a Virasoro net, contains a Virasoro net.
Less than 1.
Pardon?
Central child less than 1.
Yeah. And in particular, if you study something like, okay, I call it like that. And if in particular, you can study this with centrist charge 1/2. And then I take products. And then I can take also extensions of that. And then one can get conformal nets like the moonshine, monstrous moonshine net that was also mentioned in the previous talk. So just to say that apart from loop groups, I can deal with a huge class of conformal nets. I can't show that it is true for all, and possibly one can even get examples where it doesn't work. But at least it is fine for a very huge class of nets. And maybe the last comment I wanted to put here. So that is really a must, which I should also acknowledge since because of the chairman. So we have a very famous and strong theorem which says can identify that. So we take the fusion ring. Here we take a Lie group which need not satisfy all our conditions. So it needn't be simply connected. Okay. So in more generality, one can identify the Verlinde fusion ring with the twisted K groups, where the product here corresponds to a product, to a Pontryagin product in the language of twisted K theory. And the twist here comes from among other things, corresponds to the level. And so, in some sense, indirectly, we have using that theorem, we have a relation between these two K groups. So on the one hand, we have operator algebraic K group with a Kasparov product giving rise to determining the product here, and here we have twisted K groups, twisted equivalent K groups. And so it seems interesting to see what can be studied out of that relation. If that, what does it tell us? Okay, so that is a question with which I would like to close. Thank you very much.
Questions for Robin? It's just a curiosity. So, may one expect that there is more information on the DHR category which can be read out of K theory or KK theory, so more than the Verlinde ring, or it doesn't make sense as a question?
You mean in the sense of categories, fusion categories?
Some modular matrices or the braided structure.
One could study that. Yeah, we haven't done that, but it would be something that you could study. Of course, in that case, it is even more difficult to match the fusion category on the loop group side and the one of nets. I think in that case, we don't know it for all SUN, but only SU2. But one could try to develop something more there. Yeah.
another question? Robin again?